Today's speaker is Stefan Caporale, and he is a polymer chemist, and he's from DuPont. So we're going to pass the microphone over to him, and then we'll ask questions at the end.
Today I'm going to talk about photoresist technology. This is the chemistry that enables semiconductor manufacturing. So just a little background on myself. I attended WPI from 1994 to 98, graduated with a Bachelor's of Science in Chemistry. Prior to graduating, I did a co-op with a small electronic materials company called the Shipley Company. And at WPI, you actually take a semester off and you end up doing a 9-month co-op with the company. So you normally get a little deeper into the research. So this is my end of my sophomore year. And had a phenomenal mentor there. We really let me kind of push forward a lot. And that's actually where I got my first patent. So as far as I know, I'm still the only co-op at the company to get a patent while in co-op. And it was for, again, I worked on ion exchange resins then to remove metals from some polymer materials. I did a second co-op there on anti-reflective coatings. And then in the fall, I started working part-time there in a synthesis role before I graduated. I spent my formative years there in R&D, holding various roles, supporting various technologies. Eventually, I led to leading the R&D team that provided all of the polymer materials pretty much for the entire site. We would create between 650 to 800 novel new polymers a year to support all the various research projects going on. After doing that for quite a long time, I and some other opportunities eventually moved into the engineering teams, dealing with scale up of these same materials and the raw material engineering part of that. And then I headed the engineering chemistry team, being as the engineers wanted some chemists in their group to do that scale up. I then later on split that time with some learning data science on my own. And then now I'm actually the data analytics leader for leveraged engineering. So I'm basically an internal consultant that works for various groups around the company and helping them with data analytics and as well as my polymer chemistry background. My company has also been bought and spun off several times. So we were Shipley, became Roman Haas, we became Dow Chemical, we then became Dow DuPont, and then DuPont. So I haven't left the building, but I've changed to 5 different companies over the 24-year career. Outside of work pre-COVID, I like to travel and get around. I used to be a NAUI scuba instructor on the side. I actually stage managed and worked for them there during that vacation, and travel and cooking are my other hobbies. DuPont as a company, we spun off that about 1.5 years ago. We have 4 major divisions. I'm part of the electronics and imaging division. We have a transport and industrial division, mainly used to make, again, all the chemicals that go in your cars, aerospace, automotives, everything from brake fluid to the gaskets that are going there. We have a bioscience and nutrition and safety and construction. And in both these, we don't make a lot of final products. We make the stuff that goes into your final product. So Beyond Meat, those Impossible Burgers, we supply a lot of the raw materials to those companies that use that. Safety and construction, Kevlar, Nomex, Tyvek. We've had a lot of plants working 24/7 to make enough of these materials for the COVID response. Because again, we make a lot of the raw materials that go in the filters, the masks, and the protective clothing that the first line of the workers use. So again, we're a diverse company going from bulletproof vests for military applications to, again, ingredients into burgers and all the electronic materials, which are what I'll be talking about today, that help manufacture your semiconductors. So a quick outline of what I'll be talking about. First, just a little on transistor counts and then we'll get into the basic photoresist processing and further explain kind of the size of the transistors and what we're doing. I'll then cover the basic chemistry of all the components and then get deeper into the design of the 193 immersion resists, which are currently the state-of-the-art resist. This is what's making all the new chips for your new NVIDIA 3000 series to your new iPhone processors. And then we'll get a more in-depth look at how the process actually works and how the chemistry of the components work with each other, a few common issues, and then just a final summary. Again, most of what I work on is proprietary. So a lot of this is published information either from patents or older technology or kind of cartoon generalizations. So the transistor is the simple switch in your computer. It's the 1 and the 0 when you talk about binary. It's either on or off. And since the 70s, Moore, who is the CEO of Intel, has kind of made a marketing observation that the number of transistors, and this number refers to the amount of transistors you can fit in a square centimeter. So the average chip is about 1 centimeter squared. I know when you buy it at Best Buy or building your computer, you'll see this massive plastic piece with metals and fans and heating. Most of that's just the packaging. The actual chip inside is very small. And we're able to, every 2 years, year and a half, you would double the amount of transistors you could fit. And this is increasing the computing power, which that can do. Because the more transistors, the more math you can do quicker. And so that's what pushes forward the computer revolution. And again, this is many times throughout this chart, people would say, oh, we can't get any faster than this, or, oh, it's going to level off and go. But it's an artificial push by the industry to maintain this. And even with NVIDIA and Apple's newest chips, they're still pushing this forward. And we are actually running into some technological issues, but every time we come up against one of those walls, some new advancement tends to push it forward. Again, just for an example, your old Ataris, I don't know if any of the students remember what had an Atari. That's the first video game system I grew up with. You had about 1,000 to 2,000 transistors on those chips. Getting into my early childhood, the Genesis had about 100,000, and your first generation Xboxes, you're looking at a couple million. And then last year's iPhones, you're talking about 8.5 billion transistors, and the newest generation chip is 11.8 billion transistors in a square centimeter. So you can, and I'll get to explaining how small those are. And kind of, this is a cross section of a computer chip. So the gate or transition layer is going to be the smallest piece of that chip. And then we're going to build this transistor, as you can see, this chip up in layers. As you can see, there's all these layers. There are engineers that spend their entire life just working on one of these layers and optimizing that printing of that. This is a fairly simple chip. Your newer, again, NVIDIA 3000 series GPUs are going to be about 29 different layers. To print one layer, you're looking at anywhere from 20 to 70 process steps. And so you can start adding those up. An average piece of silicon will go into the fab, and then it'll take about 3 months to come out a chip. So if Intel needs, if Apple needs, 10 million or 5 million iPhones ready for launch, again, they're going to split that among multiple fabs and multiple production facilities and really have to pump those through. And they have to, again, start those and build them way ahead of time. So that's why, again, you'll hear that the iPhones get pushed or there gets delays and stuff like that. And again, the back end is going to be the biggest features. And then as you get to the smaller front critical dimensions, these are going to be your hardest to print smaller features. So you need to print 11.5 billion transistors all at once. You can't do that by having something print them one at a time. You have to be able to kind of transfer that in a single step. Otherwise, it would take you centuries to print them out. So this is done through a process called photolithography. So you have your substrate that is where you want to transfer your image to. And there's some other materials that go over this, which we'll get into later. And you basically put your photoresist over that. You then have a mask, which is essentially a pattern of a slide, essentially, of all the different features you want to print. So again, they have a slide with all those billions of transistors printed. They shine the light through that. Where the light hits the chromium, it doesn't go through. Where the light goes through, it hits your material. And then your material is set to either have a positive or negative reaction to that light. In a positive case, wherever the light hit, becomes soluble. In a negative case, the material becomes insoluble. You then develop it with either organic or an aqueous-based developer. You then etch the underlying substrate, then you strip off, and then you would coat copper or whatever your wires material is into the areas here, and that's how you are able to make your wires or your material that is your transistor. This is done through a very complex laser to get the focus and the resolution. Your reticle, which is that the printed image you want to transfer, is normally about 6 to 8 times bigger than what the final print on the wafer is. And the simplest equation for resolution is your resolution is a constant times the wavelength over the numerical aperture of the lens. So this wavelength refers to the size of the light we're using, and the numerical aperture is essentially the amount of light that you're capturing, very similar to, again, any other photography. So there are 2 ways that you can reduce resolution. If you can decrease your wavelength of light or increase your numerical aperture. It's much easier to reduce the wavelength of light. And for each of these technologies, these are now the older back-end technologies. Again, 157 was the plan years ago, and I'll get into kind of how that changed. And EUV is kind of the target to come in next. And then we basically just marched down the different lasers. These numbers were picked by the ability of the ASML or Nikon to make the lasers and the machines to do that. There's specific gas mixtures they were using, not my expertise. That's a gas physicist. And then we had to specifically design materials that had the other properties we needed and reacted at these wavelengths for that manufacturing. So how big are these features we're talking about? So this is an example of, this is a human hair. This would be a bacteria. And again, back in the 80s, this is what we were printing. In the 90s, we started printing things smaller than the wavelength of light that we're using. I could do an entire hour on the physics that gets into that, and that is boring even for me, but I do find it fascinating that they're able to, by using phase canceling, focus light smaller than the wavelength of light they're using. And we're looking about 80 nanometers back in the early 2000s. We're seeing 40, 2002. And again, these are when they first came into R&D use, so they don't reach production to 5 to 7 years afterwards. Sorry, that should be 2014, not 214. You're seeing 10, and you'll hear now that Intel is behind in the 7 nanometer node. That's why actually NVIDIA, who Taiwan Semiconductor manufactures their chips, is actually beating them. And that they're also, the new AMD chips are utilizing the 7 nanometer node, versus Intel is still stuck back in the 10 and 13 nanometer node. A more relevant size that I think people can understand is, if the US, we're printing an entire map of the US at once. Anything that's out of place the size of a car is going to be a defect. That's from me today, sorry. That's going to be a defect. Something the size of a pothole would be maybe a minor defect that would slow down your chip. And you're looking at a baseball being an atom. And then this is, again, we're still using 216 state-of-the-art technology now. When EUV comes into the play, where basically about 5 to 6 baseballs worth will cause a defect. So when you'll see a lot of times when you're buying a chip, it's rated at a certain gigahertz, and then the same chip will be at lower gigahertz. A lot of times that's actually the testing, and there are basically some defects that cause certain amounts of those transistors not to work, and they so bin them out, and they're able to still sell them. But again, I'm working in the technology for 20 years. I'm still amazed at how well this works. So before I talked about the resolution, we were going to march down the wavelengths of light. So something really interesting happened going from 193 to 157 then to EUV, is that for multiple years, we were working on UV resists, they're working on test EUV lasers, but the company that makes the lasers said it's not going to happen. The specific material for the lenses was unavailable at the quantities they needed to support that manufacturing. So a really neat technology, as again, this industry tends to come up with, came in to extend 193 down far enough so that we could get to EUV there. And the solution was to take the stepper, which is in a clean room where there's moisture, temperature, dust is in a Intel top of the line clean room. You're talking about 1 particle of dust per square meter. And now we were just going to shove water into it. So this was, came at a lot of fighting from the manufacturers of that's never going to work, to being the premier technology that's used now across the world. And the idea was that you put a fluid between the last lens element and the wafer. And this fluid allows you to capture more light because the refractive index coming out of this glass and the air normally causes more of that light to scatter. And so this allowed you to improve the resolution by building different lenses that allowed you to increase the NA and get down to the lower nodes before EUV would start coming into play. So now again, we have 193 immersion technology, and I'll get into some of the chemistry in a sec that enabled that, because now you're putting water over your resist, which was something that we tried to avoid for the last 40 years before that. So what makes up a photoresist? You're going to start with a solvent. You're then going to have both an acid and a base in there. The base is there to buffer the material, and then the photo acid is what starts your switch. It does what it says. When light hits it, it becomes an acid. It breaks down. That'll be referred to later in this talk as a PAG, photoacid generator. You have a very specific polymer that's built to react to the PAG. And then you have additives that adjust your film properties, and very specific to immersion is an embedded barrier layer, an EBL. And what this does is it self-segregates to the surface, making an internal protective coating so that and adjusting the water contact angle. And this is a very cool set of chemistry that's there. So the requirements for your solvents are that they're, for the most part, need to be organic solvents. For years, they tried to do aqueous water. Again, water is a great, if you use water for your chemistry, it's cheaper, it's plentiful, it's easy to purify, it's easy to dispose of. So it's always preferred, but we have to use organic based on the materials we need to dissolve. You have to cast a good film. These materials are dispensed on the wafer and spun coat, kind of like those old art projects you would get as a kid to make those spiral designs. We always are looking for environmental exposure. It's being handled in a lot of open fabs and machines where there's going to be electricity, so we don't want to work above the flash point. So it needs to be non-flammable. And again, we have to have reliable supply chain, and it has to be non-reactive with the fab equipment. We have to be able to pump this through syringes, filter materials there. Common solvents that we use are a lot of protected esters, like PGMEA or ketones. We're normally working with a blend of solvents to get the right evaporation profile to, again, get a good casting film. And that's actually one of my other things I do is I have software to model all that based on various solvent properties. The bases that we use, they have to be non-volatile and have low film migration. Triethylamine, which would be a very common organic solvent, not good because it's very volatile. It also smells bad. But you add some hydroxys on the end of that. These provide hydrogen bonding to your polymer, and you have low film migration. With this, again, you're printing very, very small feature sizes. If that material then migrates in that film and is now doing something in an area you don't want it to do. So that's, again, we want everything to stay place in that film. Same with the PAG, we need to be non-volatile, meaning that as you're heating it, it's not leaving the film. Also that it has good thermal stability. So in the areas where it was unexposed, it's not decomposing as we're baking the wafer to get the chemistry to happen uniformly. And then the acid that's formed has to be strong enough to do the chemistry we want, as well as photo efficient to the stepper that we're using. By that, I mean the, again, group that is absorbing all the light. So your benzene rings here, your group's absorbing all the light. It has to be optimized for that stepper. The more energy it takes to break your PAG apart, the longer it needs to be on the stepper, and that costs money. Because again, if you're printing 50,000 chips on a single wafer, normally we see those, it's scanning across and wants to do those in less than a second a piece, because every wafer wants to be on the stepper for a minute or two. So in the older technology for 248, which is where kind of I started my polymer days, we used a very modular approach to designing the materials. We had a backbone that is basically the reactive site to tether all the materials. We put an etch barrier, which again resists the etch step in the middle, and then we functionalized off that group here. And again, the functionalization we're looking for mainly was something that was base soluble, because they're using a base developer. So some sort of carboxylic acid or pKa hydroxy that's like phenol, about 9, that we could protect. And that way, when the acid hit it, these would deprotect. So again, the backbone had to be specific to the wavelength of the light we're using. These need to be transparent. If your polymer absorbed at the wavelength of the light you're using, then your light's never going to get through your film stack, and you're never going to dissolve away at the bottom of your film, and you won't be able to do your etch and you get your contrast. And the etch barrier is basically something has to resist the plasma etch, and that's done by a high carbon to hydrogen ratio. So the more carbon you have and less hydrogen, the etch will rip these hydrogens off and oxidize your carbons, allowing your material to ash away. So you need to have any cage groups are best for that. Wrong way. So examples of that for 248 was we used the styrenic backbone. So these vinyl styrenes react very well through here, and I'll show that in the next slide. The styrenic conjugated ring very much resists the etch process, and the pKa of the hydroxy sticking off here is about 9, making it soluble, very acidic in our aqueous to base developer. And then we can use these T-Bock protecting groups, which are very sensitive to acid, and will leave at our desired temperatures. So again, the other nice thing about these styrenic groups is their polymerizations are well studied, which makes it fairly easy for us to do. So we have our vinyl material here. We use a free radical initiator that we're able to polymerize it. You can't go to starting from directly from the phenol. That polymer reacts very, very quickly, and it will. I've blown the top off some test tubes in the lab, seeing how quick it goes. So it can be very explosive. So we actually start with the protected material, and then we go through a deprotection to remove some of this protected acetyl group and have the hydroxy, and then we protect that hydroxy further with the acid switchable group we want to use, depending on the type of resist for 248 that we're designing. Your temperature, reaction time, concentration, and the initiator loading are used to control the molecular weight of the polymer. That's your N repeat unit here, and that's just the size of your polymer. So how does the Photoswitch work? How does this switching work? Is basically our photoacid generator, when exposed to light, will form an acid. That acid will react with this protecting group here. That protecting group will give off carbon dioxide, regenerate an acid, which allows us to make this a catalytic reaction. That's partially why we need some of the base in the system that buffers this reaction from continuing to just continue and deprotect the film, as well as we get the leaving group leaving within the film, which also does help to plasticize it a little. And you can see that there's an example of the mass of the film, and this is temperature in the X direction. And with acid, as you're heating it, this will decompose and you lose your leaving group. but without acid, it's much higher. So as long as we process the wafer in the exposed areas in this process window here, we get a nice window that we can work in. You're not going to break down your PAG and your your protecting group and make it soluble. Moving to the more advanced nodes, we had to move to a methacrylate backbone. The styrenic backbone is very absorbent in 193, so that doesn't work. And so we had to go to methacrylate platform. Here we then went with more of a pendant system, and we have many more monomers we have to combine. So we have a leaving group that protects this carboxylic acid. So again, you have a leaving group that you can then expose to acid and make into an acid. This having a lower pKa, that about 4 versus the phenol, means you need less of this in your material. A lactone, these are common cage groups used for a bunch of different reasons. This functionality here will ring open once you get into your developer and make more acid. This allows you to not have your film redeposit back onto your wafer, as well as this does provide hydrogen bonding control to control your diffusion of your acids and bases through the film, as well as adhesion to your underlying substrate. And finally, it also can be in a cage format, which does provide some etch resistance. And then there's normally a cage polar and or functionalized monomer that has, again, these adamantyl cages have a very high carbon to hydrogen ratio, which allow very good etch resistance. And then again, we can functionalize off these cages hydroxys to give adhesion or other functionality as needed to tune the material. These are very unique polymers because we normally combine 4 to 6 different monomers. So I spent years learning how to and studying the reactivity of these and knowing how to put them together correctly and control that reactivity of them. Again, these are very small polymers when it comes to the size of things for any of the polymer chemists in the group. We're looking at a molecular weight, an MW molecular weight about 6,000, MN of 4,000. So you're looking about 26 to 18 molecules in that chain on average, versus, again, high density polyethylene that's used to make plastic bags and stuff is about 50 to 70,000 molecular weight. So again, these are very small but very large monomers, and that's some very unique properties. So we put all this in a jar, and again, this is the product we sell to our customers. So when they're buying it, they're getting all these materials. Normally we have a blend of 2 to 3 different polymers, 2 to 3 PAGs, 1 to 2 bases, an embedded barrier layer, and again, a blend of solvents to make it all work and play together. So again, let's look at how this process works at a more, so this is dispensed onto a wafer. So in a clean room, you have your silicon wafer, you would coat an anti-reflective coating underneath it, cure that. Again, our solvents here have to not eat away this recoating. This is so when your light gets through the film, it doesn't reflect back. And if that happens, you'll actually see the standing wave of that reflection back up, which is a pretty neat defect to see. But then you just spin this wafer, and then these materials you'll spin off essentially all the solvent, and the polymer and all your materials will be left behind. And then you soft bake that normally at 60 to 80 degrees Celsius to remove the residual solvent and get your film. So now your film is set up. The embedded barrier layer is specifically designed to come to the surface, and then your PAG, base, and base are evenly distributed out the film. This is actually one of my other patents. Again, I hold 19 patents. So an example of how these materials are made is you have a surface energy material. So normally this is a fluorinated chain. That would be under 4 carbon, total fluorinated carbons, as for the EPA's environmental PFOS reason. So again, Teflon is just this chain repeated over and over. The length of this chain, how this chain is set up, how many spacer units you have here really will dictate the contact angle with your water. And again, I can give an entire talk on tuning these angles. You have a switchable material in here. So again, this is another example of a leaving group. This allows in the exposed region you to form a lot more acid, which allows the film to be wetted. One of the first problems we ran into with this is that it was great. We can make a surface, we control the contact angle of water, but our developer is in water, and we need to have that contact the material and develop. So we realized we had to have some acid in there to let the water wet it enough, again, to tune that angle, because we don't want it completely hydrophobic to push all the water away, kind of like Rain-X on your car window. It has to touch the water somewhat, because we also don't want air gaps or bubbles forming along that, because that would scatter the light and cause defects. And then again, the leaving group in the switched areas to have good wettability. So again, this is pulled directly from our patent application, and is an example of one of the materials we use to. So in an ideal exposure, your light comes through, and wherever you have light exposed, you would form, your PAG would transform into acid, represented by the green dots here, and then you would just develop that away. But the problem is that's not what really happens. In the masks, again, because we're phase shifting to get below the wavelength of the light we're using, you get basically really intense and less intense regions. So you end up getting, in the intense regions, PAG formed all the way through the film, but in the unexposed regions, they're not truly unexposed, they're just less exposed. So they have some acid being formed. And that's one of the big reasons we put the base in these materials, is that we're buffering that top loss there, so we don't lose that film and have that acid migrate down, and you have a greater acid concentration in the exposed regions, and it's enough to overcome that buffering of the base. After your bake, your polymer in the acid region would deprotect. You can get outgassing of your leaving group, and again, depending on the fab and where it's being worked, that can be good and bad. And you don't want any of that to occur during, it's fine if it happens normally during the bake, but not during the exposure. So again, you need to make sure your chemistry is only happening after exposure on the hot bake. And again, controlling the amount that's outgassed is also something for environmental concerns. After it's developed away, you have now your pattern transferred to your resist. You then etch that away, and then you would chemically remove your photoresist. Again, I'm not an artist. Then you would plate copper over the top of that, and you would get this. You would then normally end up overplating and get that completely over the resist. And then you polish that down, which is actually a separate product that DuPont actually makes as well, which are these large pads and chemical slurries that are used to polish these wafers down and to get the uniformity across here within an order of nanometers. And then you would plate your next substrate on top of this up. And again, you would continue to build that chip, like I showed back in the beginning, up, and build all your layers and their connectivity of all your devices. So again, this is an example of a chip where they etched out all the internal material, so you could see kind of all the different wires that are in here. Here's another similar example. So you can see these aren't just, when you see a lot of the, I see a lot of the lines and spaces, this is what we print as test patterns, but these are what they're actually printing for the full-on chips. So as we're getting smaller and smaller, and as we're developing new materials, you can see this is the same resist printed at 40, 30, and 25 nanometers. And you can see as it gets smaller, you start to, this resist starts to, you start to get rounding, and then the lines start falling over. So this gives us an idea of the ideal resolution of that material, and different materials, depending on the height, the width that's here, are designed for different applications. So the amount of dose that it can take, and then a big problem is the roughness. So this is an example of some very bad roughness coming on here. And this is an example of probably the biggest issue and concern, especially as we're getting smaller and smaller, is we don't make a perfect line and space like I drew in PowerPoint. Unfortunately, you have your acid diffusion, even though it's buffered, is not uniform going across these walls. And your polymer is actually, again, because you're talking about 1 to 2 polymer chains at a place going across here. So you can see if you get this sticking out, this width of this wire is different than this width. And if you have, again, 2 wires that are too close, you're going to start getting this insulator is not going to be good enough, and you'll start getting arcing across that material, and your transistor isn't going to work as a gate. So in the next 5 to 10 years, this is the most critical parameter and problem that we're trying to solve. We approach it from 2 ends. One is the work I've done, which is the polymer improvements, which is adjusting the ratios of those monomers, designing new materials, and controlling the PAG diffusion and uniformity of those polymers. And then the second is additives to adjust the formulation and control that. And again, this is kind of a circular project. Is as my team designs new materials, the formulation team has new additives and optimizes them, and then they'll send those materials back for us to optimize a new material for those additives, and goes on and on and on. So it's constantly pushing this down to there. Just to give you guys an example of how small this is, 1 polymer is about 3 nanometers big. So we're getting to the point where 1 polymer chain at a place is really where we're starting to have to kind of control. And so we started to make smaller polymers, as well as come up with polymers that unzip or scission along there. So that's my quick and dirty look at kind of how semiconductors are manufactured. We've gone through an overview of the process. I went over the kind of basic chemistry that we're utilizing, and kind of the roadmap, and kind of we are reaching the end at EUV. There is no optical lithography option after EUV. So a lot of the next generation chips are starting to look at new novel chip designs. They're starting to try to work more wavegates to use light rather than electricity to move in there. And no one has the right solution yet. The industry hasn't decided on one. So it's a big, wide open field right now. And a big part of academic research right now is looking at what are these next things. They're using self-segregating polymers that auto-align. The Wilson group and the Verche group are looking at those out of UT and Berkeley. That's there. So I open it up to any questions, comments, disagreements from the class.
Great, thank you. We do have a couple questions here. Feel free to put some more questions in, and this is a good time if you need any clarifications in the notes that you took. Feel free to put those questions in here too. So the first question is, do you only work with the creation of transistors? And if so, what step of the process do you specialize in? And do you hold a broader position where you help with many stages of creation or a more specific stage?
So the technology used, so we create every piece of that chip. Our chemistry is used to make every piece of that chip. The transistors are the most critical, meaning that they're the smallest feature on the chip. So that's the state-of-the-art material. And so whatever is state-of-the-art today starts to move back in the chip as it becomes older technology. So at one point, the gate was this big, and this was state-of-the-art technology, and the back-end interconnect was much bigger. So 248 at one point was the gate, then it moved back to these layers, and now it is pretty much, and like same with 193 was the gate, it moved back, and now 193 is putting a lot of these layers, 248 up here, and then I-line, G-line. Our Brennan, we still sell much more volume of the older technologies. Also, it depends what type of chip you're trying to build. So if you're building a commodity chip that you're selling, like an oxygen sensor in a car that you're selling for 35, 40 cents a chip, you need to make that A, very cheaply, and B, it needs to do that, you also have to have not rework it. The technology has to be work and be very good. So yeah, we enable all the pieces that are there, not just the transistors. The transistors are just the fun part because they're the hardest to do. And that technology is going to be the first in the fab, and then they'll start spreading it every places. It's very rare they'll use a new resist for a older technology. So whatever you win at the transistor level is going to slowly work its way back into the resist. You might slightly tweak it, but it's going to be of the same family because they already learned how to use it and image it when the best of the best are doing the transistor and the hardest to do images.
Great, thank you. When discussing solvents, you had mentioned that water is a good choice in part because it's environmentally friendly. How safe for the environment are other components of this technology? Are there plans to develop any alternatives?
So we have, starting the semiconductor industry actually stays, I would say, 5 to 8 years of the EPA's and most other countries' restrictions. Our ban list is much longer than what the EPA requires us to do. And that's because once the technology is being used, so much money has gone into inventing it, developing it, and then the processing for it. Those companies don't want to ever stop using it. So they will preemptively switch out materials. And most of the time, the green initiatives that companies have, those are also normally very green money-wise, because normally the alternatives are not as costly, because anything that's not environmentally friendly costs a lot to dispose of. And we're using a lot of these materials within the manufacturing. If we can do something that's easier to dispose of, and easier to work with in manufacturing, which requires less PPE, or easier to handle, those all reduce the cost of our materials. But the biggest thing I would say is that we got rid of long fluorine chains well before Teflon and any other industry started worrying about those. Halides and other those materials were stripped out and not used even 2 to 3 steps away from the final product because they don't want to even have them in trace amounts. Formaldehyde was phased out in the early 90s, where in a lot of manufacturing, carpets and stuff, it's still being used in a lot of things. So because of the cost of switching the technology, Samsung, Intel, all the big fabs stay way ahead of any government regulations and environmental concerns.
Next question is, what makes the water organic? Does that mean it just has carbon in it since water is considered inorganic?
Correct. Water is an inorganic aqueous, any chemist. So water is considered technically an inorganic solvent. We need an organic solvent, which has carbon and oxygen in it, to use. That's because most of those solvents have the properties we need. If there was an inorganic solvent that met all the properties we need, we'd have no problem using it. Just that, and like everything in this industry, once they're safe and happy with a material and we have a supply chain that meets our needs, it's very tough to go outside the box and use, especially a solvent that's new. And so there's maybe in my 24 years of working on this, we've introduced in final products maybe 7 new solvents that have been brought in to be used, which is not a lot because, again, in the final products in those fabs with all that equipment, they want to make sure it's the same. They don't like new things. And we have a very strict low metals, and there's a lot of technical specs we have to meet. So we have very few suppliers that can meet those specs.
With the technology we currently have, what makes specific chips work better than others?
So that's more of a chip design piece, and has to do with depending what the chip is meant to do. Part of that too is that it's the heat. Right now, a big piece of research, whole different group downstairs and on the other side of the building, is helping with the heat reduction. So when you run electricity through these chips, you create heat. And that heat, as the chips get hotter, they become less efficient at getting, as a piece of metal gets hotter, it becomes less efficient at pushing electrons through it. And you can imagine if you have this piece of metal that's only a couple nanometers big, eventually, if you push enough energy through it, you're going to cause problems with that piece of material, that it's not going to be able to handle all that energy through it. So the heat dissipation is a very big piece of, if you can put more energy through that chip and get rid of the heat, then you can run it faster. That's why you hear a lot of liquid cooled stuff is becoming actually a standard for a lot of the new NVIDIA chips. You have to have liquid cooling. And a lot of that's also in the design architecture of the chip to allow access to dissipate that heat there. But that's more the design rather than the chemicals going in to manufacture them.
Next question. What company has the 7 nanometer advantage?
TSMC, Global Foundries are and UMC are the big ones producing that now. So AMD, NVIDIA, they don't make their own chips. They are what we call virtual chip designers. So they design the chip and then they go to a foundry, which is someone like TSMC is probably the most well-known, that TSMC just has processes and learns how to make chips. And then other people contract them to make chips for them. And versus Samsung makes their own chips. Apple, again, doesn't run their own foundries. They design them, but other people make them. Actually, Samsung makes a lot of Apple chips, which always cracks me up that Samsung and Apple are suing each other over the iPhone versus the Galaxy because they rely on Samsung to make a lot of their chips. But Intel is the biggest foundry. Intel makes their own chips, and they're the biggest chip maker, probably the most prominent, that is behind in that technology. And they've actually, in their most recent earnings call, talked about outsourcing some of those either layers or entire chipsets to either TSMC or some of their other foundries for hire.
Great. Are there any polymers you've created that have been unexpectedly volatile or unstable?
No.
Easy answer.
I have made smoke come out of the top of a reactor. That was not because the polymer was unstable, it's because the reaction went too quickly when we scaled it up. But again, it was which is why we do scale up chemistry, is that we have a computer controlled reactor, so I was not near it. It has safety set up and probes in there to record the temperature and everything. So as it overheated, the active cooling came in, little smoke came out the top, right out the fume hood that it was in. There was no safety issues around that. And again, we had to redesign the synthesis from that because it was actually, and again, an interesting discovery that at a certain scale, the heat distribution, again, between the reactor design wasn't enough. And again, that's why you don't go from 10 grams to 20 kilos in one shot. You go 10 grams, then 50 grams, then 500 grams, then maybe a kilo or two, and you do calorimetry and you look at how those reactions work.
Great. That looks like our last question. Anybody has any final thoughts? Oh, here's another one. Sorry, one more. The liquid layer above the arc was thinner. Would the pattern be printed with higher resolution, for example, less ragged lines, because there would be less dispersion?
The liquid layer is above the resist, and that's squished between the lens. So the thickness of that, we've tuned our resist, and they've tuned the optics for a specific thickness. So that's all been optimized by the lens developers and the physicists there for the right resolution. So I don't know if part of that is you have to control that layer. And again, that layer is, again, nanometers thin. I think it might be, it's fairly big. It's like, I think a centimeter or so, but it's not ginormous. But again, that's optimized by the people who designed the lens. And there's actually a curtain of nitrogen that holds that water in as the material moves around. But again, our job is just they have the standardized format for the lens, and we just design the material to work with their design.
And just a request, if you could just repeat your official job title.
So now I am the data analytics leader for emerging technologies. I literally was moved to this new role in July during COVID. So I got a new boss during July. And I split that time, but I still advise groups on, I'm still a very well-versed polymer chemist. I made multiple thousand different photoresist materials and helped scale them up. So I still lend out that expertise as needed within the company. I'm kind of currently working as kind of an internal consultant to a bunch of different groups. Or subject matter expert is what they would call them.
Great. Any other final questions? All right. Think that'll do it.
Okay.
So thank you so much for your presentation. It was really different from the other presentations. Well, I feel like every presentation we've had has been really different, but keeps it interesting. Definitely a topic that hasn't been covered. So we appreciate your time and your expertise and for joining our class.
All right. Well, thanks for having me.
Thanks, everybody. We'll see you next week.